Okay, so what we have here is chapter 37, figure 37-3, and then we also have figure 37-8, and these pictures go right along with it. We have something specifically that we should mention here is Faraday's law, and Faraday's law is this idea right here, which we'll talk about these loops here that we'll talk about in a second. The basic idea is that I have a voltmeter, and this one is millivolts, so it's very sensitive. And this is a lab or a demo you can do in class. There's one of those electromagnet type setups with no battery, and no battery at all. But it's the wires themselves are connected to the black and red connections, and there's simply a coil of wire, and then we have strong magnets. If you don't touch this, don't move the table so this wiggles, just don't touch anything, just close to the coil, move these magnets back and forth, and you'll see without touching anything, this will begin to deflect back and forth. It's creating a voltage potential. And really what that's doing is, it is doing induction. It will induce electrons to move. Literally, you'll be pushing electrons with the force field. So the magnetic field is interacting with the electrons, and it's pushing them along the wire. The more coils you have, the stronger the force. And so this picture is showing you that this is the potential, or the electrical potential that's created, otherwise known as voltage. When you move this through this double coil, it'll be twice as much in this through a quadruple coil, and it'll be again increased by more coils here. So Faraday's law says the induced voltage in a coil is proportional to two things. It's proportional to the product of the number of loops, so counting the number of loops, and then also the rate. So that's why Folsom Dam, for instance, doesn't just have lots of loops, but it has lots of loops of wire, and it also spins very fast. So that's Faraday's law. Says that you'll get more electricity out of something if you have more coils and faster magnetic motion. So here I have the same exact idea. This is a magnet, and it goes back and forth between these coils. The more coils, the more electricity, and the faster you move that magnet back and forth, the more electricity you get. That's Faraday's law. So moving on to what a generator is then, a generator takes the idea of induction, and it says, okay, if I have these wires and I move them next to this strong magnet, I can induce a current to flow through the wire, and I can use it to power something like a light bulb or a computer or whatever. So you have a source of motion. It could be steam from nuclear. It could be steam from burning coal, right? So you want to have some source of energy. And we're going to burn coal, make steam, and the steam will turn this turbine. That's where most of your energy comes from. However, it could also be a waterfall, like a dam, right? It could go by this way, and it could spin it. Or it could be wind. And so you could have wind power, and you could have a windmill. So really what we want is we want some sort of a mechanical energy, and this is the motion here. The steam or the water or the wind is mechanical energy that's going to turn this wire. You can do it by hand if you want to as well, like with my exercise bicycle in class. And when it turns these wires, this armature system, these wires are in the magnetic field, and it will push the electrons through the wire into your appliance. And of course you have to have a circuit, so it has to go in a circle. And so the electrons will begin to flow. And that really is what electricity is. If you didn't have the magnets and you just spun the wires, nothing would happen. The electrons wouldn't be pushed by anything. You have to have the magnets there to push on the electrons as you spin it. So magnets, spinning, loops, lots of spinning, lots of electricity. And that's basically the story of how you make generators, or how you generate electricity. The word here to remember is induction. We are inducing a current across a wire.